today's video lecture, we are going to see section 3.3, which is headed the second derivative and concavity. You can see in the first box an important statement which we are going to use throughout the section. It says that the sign of the second derivative indicates which way the graph of a function is bending. So in order to see how a function graph is bending, we will use the second derivative. That's what the statement says. As a quick recap, we already mentioned critical points in the last section. Critical points are those points such that f dash of those points is equal to 0. Okay. And also we mentioned the increasing decreasing test which said f dash of x naught is strictly greater than 0 will imply that the function is increasing at x naught. F dash of x naught is strictly less than 0 will imply f is decreasing at x naught. And also the test cannot be applied, or the test is not conclusive when f dash of x naught is equal to 0. That's some among the points which we discussed in the last section. So you can see two figures here, and you can see the bending of the function. See here the function is bending like this at this point, and here in this function is bending here first and then bending here first. So we are going to watch out how this bending can be associated with the second derivative or f double dash of the function. And also to recap some among the details in the last section, as we said, f x naught is a critical point, then f dash of x naught is equal to 0. If f dash of x naught is strictly greater than 0, we said that the function is increasing at x naught, or we can say that f changes from a negative value to a positive value at x naught. Similarly, if f dash of x naught is strictly less than 0, then we say that f changes from a positive value to negative value at x naught. And when f dash of x naught is equal to 0, the test is inconclusive. We cannot conclude. Similarly, if f double dash of x naught is equal to 0, then x naught is a critical point of f dash. If f double dash of x naught is strictly greater than 0, we can say that f dash changes from negative value to positive value at x naught, which means that x naught is a local minimum. This we had mentioned before. If f double dash of x naught is strictly less than 0, we can say that f dash changes from positive to negative value at x naught, which means that x naught is a local maximum. And also when f double dash of x naught is equal to 0, the test is inconclusive. We cannot conclude what happens there. So the second derivative test is sum up from what we said in the end. Suppose that f dash of x naught is equal to 0, then f double dash of x naught strictly greater than 0 will mean that x naught is a local minimum point. If f double dash of x naught is strictly less than 0, then x naught is a local maximum point. And if f double dash of x naught is equal to 0, we cannot conclude about the test. We can understand the concept from the examples. Example 1, use the second derivative test to analyze the critical points of the function f of x is equal to x cubed minus 6x squared plus 10. So we are given the function f of x is equal to x cubed minus 6x squared plus 10. So f double dash of x is equal to 3x squared minus 12x, right? Which is equal to 3x into x minus 4. First step is to find the critical points. So f dash of x naught is equated to 0. That will mean that 3x into x minus 4 is equal to 0. So the points which are critical points are x naught is equal to 0 and x naught is equal to 4. Now f double dash of x is found from this. You get it to be equal to 6x minus 12, and we are going to apply 0 at these f double dash of x. So f double dash of 0, you get it to be minus 12, which is strictly less than 0. And also f double dash of 4 is equal to 24 minus 12, which is equal to 12, which is strictly greater than 0. So you can conclude from the second derivative test that 0 is a local maximum point and 4 is a local minimum point. That's how we wind up example 1. Next, you can see example 2. The question is, analyze the critical points of f of x is equal to x cube minus x. So here you have function x cube minus x. So f dash of x is equal to 3x square minus 1. We are going to equate it to 0 to find the critical points. Okay, when equated to 0, you get 3x square minus 1 is equal to 0. Divide the whole equation by 3, you get x square minus 1 by 3 is equal to 0. Then it is of the form x square minus y square on the left. So you can write it as x plus y into x minus y, x square minus y square. Here y square is equal to 1 by 3. So y will be root of 1 by 3 or 1 by root 3. So you can write in the left hand side x plus 1 by root 3 into x minus 1 by root 3 is equal to 0. So you get x is equal to plus 1 by root 3 and minus 1 by root 3. Both are coming from there. Then you write f double dash of x, that is equal to 6x. Okay, then substitute the critical points inside this f double dash of x. So here you have first of all f double dash of 1 by root 3. When you substitute, you get 6 by root 3. 6 can be written as 2 into 3, which is root 3 into root 3. Cancel out the root 3's from the numerator and denominator. You get in the end 2 root 3, which is strictly greater than 0. From the second derivative test, you get since f double dash of 1 by root 3 is strictly greater than 0, you get x naught is equal to 1 by root 3 is a local minimum. Similarly, f double dash of minus 1 by root 3 is calculated. You get that to be equal to minus 2 root 3, which is strictly less than 0. So x naught is equal to minus 1 by root 3 is a local maximum by the second derivative test. So that's how we conclude example 2. Now let's see example 3. Analyze the critical point x naught is equal to minus 1 of the function given f2x raised to 4 plus 8x cubed plus 12x square plus 8x plus 7. We are given the critical point x naught is equal to minus 1. Let's see how we can obtain that. How did the critical point come? How did we manage to do it? We have f of x, then you find f dash of x, then equate f dash of x equal to 0. You get 8x cube plus 24x square plus 24x plus 8 is equal to 0. You can divide the whole equation by 8. You get x cube plus 3x square plus 3x plus 1 is equal to 0, which is the expansion of x plus 1 the whole cube. So you get in the end that x plus 1 the whole cube is equal to 0. That means x is equal to minus 1 minus 1 minus 1. So x is equal to minus 1 is only a possibility. So that means minus 1 is a critical point of the function. Next you calculate f double dash of x. You get 24x square plus 48x plus 24 as f double dash of x. Then you put the critical point inside this f double dash of x. So f double dash of minus 1 is calculated. You get that to be equal to 0. So you cannot conclude here because the test cannot be used here because f double dash of minus 1 is equal to 0. So how will we manage? What we do is, you know that minus 1 is in between minus 2 and 0. So what you're going to do is, you are going to find f dash of minus 2 first. Okay. Uh, Here you have to actually find about minus 1. You're going to find the value of f dash at a point to the left of minus 1, which is we are going to take it as minus 2. So f dash of minus 2 is calculated, you get that to be equal to minus 8, which is strictly less than 0. And to the right of minus 1, we choose the point 0. Okay, you can choose any point to the right of minus 1. I am going to choose 0. So when you find f dash of 0, you get that to be equal to 8, which is strictly greater than 0. So to the left of minus 1, you get that f dash is strictly less than 0. And to the right of minus 1, you get f dash is strictly greater than 0. So f dash is changing from negative to positive at minus 1. So as we had mentioned while we were doing the recap, see, when f dash is changing from negative to positive, x naught is a local minimum. F dash is changing from positive to negative, x naught is a local maximum. So let's see what we obtained here at the neighborhood points. We got f dash is changing from negative to positive. That means it is a local minimum point. That's how we conclude when we cannot use the test. You'll use the neighboring points to the left and right and find the values, how the change of the sign is coming, and then conclude. Okay. So you can see in the first figure here that the function drawn is concave upward. The shape, you might have heard about concave lenses, convex lenses, like that. Here this is called concave, and this is concave up, and this is called concave down. Okay, the first is concave upward and the second is concave downward. And we already discussed about linear approximation in the earlier sections. Suppose you have a function f of x. You talk about the linear approximation of f of x at x naught as call it L of x is equal to f of x naught plus f dash of x naught into x minus x naught. Okay. Suppose if f of x is strictly greater than L of x for every points inside an open interval AB where AB has inside the point x naught. Okay, that means f of x naught minus L of x naught is strictly greater than 0. At that point, we say that f is concave upward at x naught. That's how we define concave upward in another manner. Okay. Similarly, when f of x is strictly less than L of x for every point inside an open interval AB, where AB contains this x naught, then we say that f of x is concave downward at x naught. So that is an important definition you get from this paragraph. See, you can read the same from this paragraph. That's what we have written here. Some more information from the next paragraph. Suppose if we are defining the difference of f of x and L of x as h of x, that is h of x is equal to f of x minus L of x. When f of x is strictly greater than L of x, that is when the function is concave upward, you get h of x is equal to f of x minus L of x, which is strictly greater than 0. Okay, that is equal to f of x minus, substitute the equation for L of x, you get that to be equal to f of x naught plus f dash of x naught into x minus x naught. When you open the braces, you get that to be equal to f of x minus f of x naught minus f of x naught into x plus f dash of x naught into x naught. To repeat, When you open the braces, you get that to be equal to f of x minus f of x naught minus f dash of x naught into x plus f dash of x naught into x naught. Now take the derivative of h dash of x. So you can take the derivative of this expression with respect to x. So when you take the derivative of f of x, you get f dash of x. When you take the derivative of f of x naught, it is a constant, so that will be 0. Here f dash of x naught is a constant, but x is the variable, so you can take the constant to the left, and then that is d by dx of minus f dash of x naught into x will be equal to minus f dash of x naught into d by dx of x, which is equal to minus f dash of x naught into 1. So that's what we get there. See, here you have f dash of x naught. Here, both of them are constants, so you get in the end that h dash of x is equal to f dash of x minus f dash of x naught. Now, to calculate h double dash of x, you get that to be equal to f double dash of x, because f dash of x naught is a constant. Now, we are going to say that h dash of x naught is equal to 0. That will mean f dash of x that is equal to 0. Why? Because h dash of x naught, when you substitute x naught here, that will be equal to f dash of x naught minus f dash of x naught, which is equal to 0. That means x naught is a critical point of the function we defined, h. Okay. Also, h double dash of x naught is equal to f double dash of x naught, right? So, x is a local maxima for h when h double dash of x naught is strictly less than 0, or you can say that f double dash of x naught is strictly less than 0. Similarly, x naught is a local minimum for h if f double dash of x naught is strictly greater than 0. That's some conclusions we derive from the two paragraphs there. And to talk about the second derivative test for concavity, the first one is if f double dash of x naught is strictly greater than 0, then we say that f is concave upward at x naught. If f double dash of x naught is strictly less than 0, then f is concave downward at x naught. If f double dash of x naught is equal to 0, then f may be either concave upward at x naught, concave downward at x naught, or neither. Okay. So let's discuss the same test with some examples so that you can get the idea a little more better. Example 4, discuss the concavity of f of x is equal to 4x cube at the points x is equal to minus 1, x is equal to 0, x is equal to 1. So given that f of x is equal to 4x cube, that will imply f dash of x is equal to 12x square. That is f double dash of x will be 24x. Okay. You're given points minus 1, 0, 1. So if double dash of minus 1 is calculated, you get that to be equal to minus 24, which is strictly less than 0. By the test mentioned before, that means f is concave downward at x naught is equal to minus 1. And f double dash of 0 is equal to 0. That means we cannot arrive at a conclusion by the test according to which the test is given the third point. Now f double dash of 1 is equal to 24, which is strictly greater than 0. That means f is concave upward at x is equal to 1. Now f dash of minus 1. F dash of minus 1 is equal to 4 into minus 1. Yes, here f dash. There is a slight variation. When f dash of minus 1, you get that to be equal to f of minus 1 is equal to minus 4, f of 0 equal to 0, f of 1 is equal to 4, which is strictly greater than 0. That means our function is having a negative value to the left of 0, and then it has positive value to the right of 0. That is, you can say that f is increasing at 0. Okay. Also, we can say that if this is the function, if this is the function drawn, and this is the tangent line, okay, the function crosses the tangent line at 0. That means the function is not above the tangent line or below the tangent line, because it is crossing the tangent line, right, at 0. So you cannot say that f is concave up or concave down. That is what we conclude is f is neither concave up nor concave down at 0. So that's example 4. Now example 5 asks us to find the intervals um, where f of x is equal to 3x cubed minus 8x plus 12 is concave upward, and on which it is concave downward, and we are asked to make a rough sketch of the graph. So given the function f of x is equal to 3x cubed minus 8x plus 12, f dash of x will be 9x square minus 8, f double dash of x will be 18x. When x is strictly greater than 0, you get that f double dash of x will be equal to 18x, which is strictly greater than 0. From the test which we mentioned at the start of the session, you get the function is concave downward whenever x is strictly greater than 0. And similarly, when x is strictly less than 0, you get f double dash of x is equal to 18x, which is strictly less than 0. That is, the function is concave upward for every point x strictly less than 0. Now let f dash of x is equal to 0. You have f dash of x is equal to 9x square minus 8. Equate it to 0. You get x square minus 8 by 9 is equal to 0 when we divide the whole equation by 9. And you know it is of the form x square minus y square. It can be written as x plus y into x minus y. Here y square is equal to 8 by 9. That means y is equal to root of 8 by 9. So you can split the LHS as x plus root 8 by 9 into x minus root 8 by 9, which is equal to 0. Root of 8 by 9 can root of 8 is equal to root of 2 into 2 into 2, which is equal to root 2 into 4, which is equal to 2 root 2, because 4 root of 4 is 2, and similarly root of 9 is 3. So you can simplify root of 8 by 9 as 2 root 2 by 3. So in the end, what you get as critical points are plus or minus 2 root 3, 2 root 2 by 3. Okay. So here what you are going to do is you have the function f dash of x is equal to 9x square minus 8. Okay. So first of all, you're going to take minus root of 8 by 9, that is minus 2 root 2 by 3. Okay. Minus root of 8 by 9 will come strictly in between root of minus 9 by 9 and root of minus root of 9 by 9 and minus root of 7 by 9, right? So you're going to take the left one, that is minus root of 9 by 9, which is equal to minus 1. So f dash of minus 1 is equal to 9 minus 8 is equal to 1, which is strictly greater than 0. Now similarly f dash of minus 7 by 9, which is equal to 9 into 7 by 9 minus 8, which is equal to minus 1, which is strictly less than 0. So you have the sign changing from positive to negative. That means you have a local maximum at minus root of 8 by 9 or minus 2 root 2 by 3. Now for root of 8 by 7, root of 8 by 9, you're going to consider the intervals, the points to the left as a root of 7 by 9 and the point to the right as root of 9 by 9. So take f dash of root of 7 by 9, you get 9 into 7 by 9 minus 8, which is equal to minus 1, which is strictly less than 0, and f dash of 1 is equal to 9 into 1 minus 8, which is equal to 1, which is strictly greater than 0. So the sign is changing from negative to positive. Therefore, you are having a local minimum at the point root 8 by 9 or 2 root 2 by 3. So you got how the function is bending, how the concave upward and downward are coming at the point. So you'll just have a rough sketch like this. Here minus 2 root 2 by 3 is plotted here, 2 root 2 by 3 is plotted here. We said that at minus 2 root 2 by 3, the function is concave downward. That's what you got at the first. See, for the positive values, the function will be concave downward, and for negative values, the function will be concave upward. For this point, definitely the function will be concave upward. And we said that x is equal to minus root 8 by 9 or minus 2 root 2 by 4 by 3 is a local maximum. So here we gave it a local maximum. This is a local maximum point, this one. And similarly 2 root 2 by 3 or root 8 by 9 is a local minimum. So that's why we got it like that. So this is how we draw the rough sketch of the function given after analyzing the inferences. So the next topic is called inflection points. So here in this example, which we just have arrived at after our calculations, here you can see that the function is going up like this and then it is going to go down, right? It was moving concave upward and then it is going concave downward. Okay. So here there is a change of the behavior of the function. Right. The bending is changing at some point, called this point, where the cursor is seen. Okay. That point, we understand that the function is bending there to change the behavior. Such points are called inflection points. Or to officially define an inflection point, we can say that an inflection point for a function f is a point where f double dash changes sign. Okay. Or if x naught is an inflection point for f, that will imply f double dash of x naught is equal to 0. Or if f double dash of x naught is equal to 0 and f triple dash of x naught not equal to 0, then x naught is an inflection point for f. So you have three definitions from there where which you can use in your problems. First says that an inflection point of for f is a point where f double dash changes sign. Okay. Second says if x naught is an inflection point, then f double dash of x naught is equal to 0. Okay. Third point says if f double dash of x naught is equal to 0 and f triple dash of x naught not equal to 0, then x naught is an inflection point for f. Okay. So in this example, of figure drawn here, we can see that the function is moving down like this and then changing its behavior here. So this point is an inflection point. Similarly, the function was moving up and then changes to moving down behavior. So this point gives the change. So both these points are inflection points. The corresponding value in the domain are x1 and x2. So these 2 points are inflection points. In example 6, we have to find the inflection points of the function given. So for this question, you can see that the function given is x square plus 1 by x. So when we calculate f dash of x, you get f dash of x is equal to 2x minus 1 by x square, right? Just written here. Okay, so the second derivative implies f double dash of x is equal to 2 minus 2 divided by x cube plus, right? Okay, 2 plus 2 by x cube. So you're going to equate f double dash of x is equal to 0 to get the inflection point. If this is equal to 0, you can take 2 out. So you get 2 into 1 plus 1 by x cube is equal to 0. Therefore, 1 plus 1 by x cube is equal to 0, which means that um, 1 by x cube is equal to minus 1, or what you get from there is x cube is equal to minus 1. Therefore, x is equal to minus 1 is the choice. Okay. So, x is equal to minus 1 is a possibility for inflection point. Um, to test whether it is an inflection point, you just find the third derivative. So the third derivative will be minus 6 by x raised to 4, right? So put this minus 1 in this function. That is f triple dash of minus 1 is equal to here f triple dash of minus 1 is equal to minus 6 by minus 1 the whole raised to 4, which is equal to minus 6, which is strictly less than 0, and which is not equal to 0, right? So by definition you get that x is equal to minus 1 is an inflection point of the given function. And the definition of the function says that if f double dash of x naught is equal to 0 and f triple dash of x naught is not equal to 0, then x naught is an inflection point. There are chances that if f double dash of x naught is equal to 0 and f triple dash of x naught is equal to 0, there can be inflection points for f. That is what is written in this paragraph. If f double dash of x naught is equal to 0 and f triple dash of x naught is equal to 0, then x naught may or may not be an inflection point, because this is not an if and only if condition, right? This is only a one-way condition. If both of them happens, x naught is an inflection point. And if both of them doesn't happen, it doesn't mean that x naught is not an inflection point. Okay. So there is possibility that x naught is an inflection point even though f double dash of x naught is equal to 0 and f triple dash of x naught is equal to 0. That's what we are going to see here. Suppose if f of x is equal to x raised to 4. That means f dash of x is equal to 4x cube, f double dash of x is equal to 12x square, f triple dash of x is equal to 24x. As we mentioned now, when we find f double dash of x is equal to 0, you get 12x square is equal to 0. That means x square is equal to 0. You can say that this x is equal to 0 may or may not be an inflection point. You can calculate f triple dash of 0. That is 0. Okay. Now, if x is strictly less than 0, find f double dash of x. That will be 12x square, which is strictly greater than 0 because it is x square. For any x less than 0, also x square is positive. Similarly, if x is strictly greater than 0, f double dash of x is equal to 12x square is strictly greater than 0. So, as we move from the left to the right, in considering 0, there is no change in sign. So we cannot say that it is an inflection point, or we rather say that x is equal to 0 is not an inflection point. Uh, in this case, it is not an inflection point. Now take another function f of x is equal to x raised to 5. This is the first function we are talking about in this para. This is the second function we are talking. Here it is the example which says that the point may not be an inflection point even though both are zeros. Here this example says that the point can be an inflection point even if f dash of x, f double dash of x and f triple dash of x is equal to 0. Suppose if f of x is equal to x raised to 5, that implies f dash of x is equal to 5x raised to 4, implies f double dash of x is equal to 20x cube, implies f triple dash of x is equal to 60x. So to find the inflection point, first equate f double dash of x is equal to 0. That implies 20x cube is equal to 0. Therefore, x is equal to 0 may or may not be an inflection point here. When we calculated f triple dash of 0, you get equal to 0. So you cannot apply the test. Now you take x strictly less than 0. So that means f triple dash of x is equal to 60x. That will be definitely strictly less than 0. Also, if x is strictly greater than 0, f triple dash of x is equal to 60x is strictly greater than 0. That means the sign is changing from negative to positive. There is a change in sign for this uh, f triple dash. So here you get that x is equal to 0 is an inflection point of the function f of x is equal to x raised to 5. And this is, yes, there is a little change there. This is x square. So here you are going to use, there is a change there. You are using f double dash of x as we mentioned here. Okay, here is f double dash of x will be 20 x cube. Okay, so yes, even that serves a purpose. That is strictly less than 0. Here this is equal to 20 x cube. That is strictly greater than 0 when x is positive. Okay, so the sign is changing from, yes, the sign is changing from negative to positive. That is again an observation there. There's a slight change there. That is, the sign is changing from negative to positive. So there is a change in sign. That means x is equal to 0 is an inflection. So note that f double dash of x is what we used. Okay. So here you got that even though f double dash of x naught is equal to 0, f triple dash of x naught is equal to 0, then there are two possibilities that x naught is not an inflection point and also sometimes x naught is an inflection point. There are two possibilities. That's what we just saw from this paragraph. Now you can see example 7. Find the inflection points of the function f of x is equal to 24x raised to 4 minus 32x cube plus 9x square plus 1. So you have the function we have the function f of x is equal to 24x raised to 4 minus 32x square plus 9x square plus 1. Okay, when you have this f dash of x, when you calculate it, you get that to be equal to 1 that will be equal to 96x cube minus 96x square plus 18x, and f double dash of x will be equal to 288x square minus 192x plus 18 when you calculate, and f triple dash of x will be 576x minus 192. So the first step is, in order to find the inflection point, is equate f double dash of x is equal to 0. So when you equate, you get 288 x square minus 192x plus 18 is equal to 0, implies 48x square minus 32x plus 3 is equal to 0. That is, you divide by 6, you get this. And then use the quadratic equation, which is equal to, that is x square plus ax square plus bx plus c is equal to 0, implies x is equal to minus b plus or minus root of b square minus 4ac by 2a. We are using it here. So you have the b, a and c here. Substitute them, and when you calculate and evaluate, you end up with this 4 plus or minus root 7 by 12. So you have 2 points, 4 plus or minus root 7 by 12, 4 plus root 7 by 12, and 4 minus root 7 by 12. And here we are concluding in this example by saying that by the knowledge of parabolas, we can conclude that f double dash changes from positive to negative at the first point and from negative to positive at the second point, which says that both of them are inflection points. Also, another way is to evaluate f triple dash of 4 plus or minus root 7 by 12. You can use that method too. Use your calculator. You can substitute 4 plus or minus root 7 by 12 inside f triple dash of x and say that it is not equal to 0 in both cases. That means both of them are inflection points. That is one method. I think you can leave the other method because that might be little confusing for you. Okay, as as a work, I'm going to leave you with f triple dash of 4 plus root 7 by 12. You have to find it using your calculator. And also f triple dash of 4 minus root 7 by 12. Find what it is and say that both are not equal to 0, means both of them are inflection points from what we defined just before. Now, example 8 asks us how you can classify the points given in the figure. Here you can see that x1, this is a local maximum point, okay, and x2, you can see that the function is changing its sign from here to here. That means it is an inflection point. Similarly, x3 is also an inflection point. And x4, when you consider it, since f of x4 is equal to 0, we cannot say that it is any of these. Okay, and this x5 is a local minimum point and x6 is a local maximum point. That's example 8. Okay, and you have to go through all these ideas, and you can solve 1, 4, 5, 8, 10, 13, 15, 18, 24. In this exercise, make sure you understand what the new definitions are. We have introduced the inflection points in this section, and also the secondary derivative test. which talks about concavity and how the bending of the function is occurring when we draw a graph. So make sure you are thorough with what we discussed today and work out the problems and submit in the link which are assigned to you. So thank you for watching out. See you in the next lecture.